So this is the problem on the Wheatstone Bridge, and when we look at it, it kind of looks like these two here are in parallel with each other and these two are in parallel, and of course this one comes after that, but there's a junction in between. And this one here, if you really think about it, is neither in parallel nor in series with any of the other resistors, and that also means that these here, I said, they look like they're kind of in parallel to each other, but because of this one here, it's really hard to tell. For example, you could say that the current flows through here and through here. So despite the junction here, this could be here kind of in series and parallel with this one. But then again, the current could flow through here and there. And it kind of looks like these two are in series and parallel with that one. So you cannot make a decision on it. And therefore, the typical series parallel combination circuit analysis is not going to work on this one here. And it has to be Kirchhoff's rules. I get to Kirchhoff's rules here in a moment, but first I want to put that on the circuit construction kit. Actually, even before I do that, I should actually read what the problem says, and that is, the circuit in the drawing is known as a Wheatstone Bridge circuit. Find the voltage between points B and D and state which point is at a higher potential. Find voltage. Okay, so looking at this one here is actually, this is where we have to find the voltage and where we have to determine which is at the higher potential. Okay. So I'm going to click on the construction kit, and that'll take a moment to open. So this is of course from PhET, Physics Educational Technology, from University of Colorado in Boulder. Alright, grab a wire. Actually I'll grab a number of resistors, and it doesn't really matter if I do it like this or if I do it like it does in there. Actually, come on. Might just make it look look nicer if I do it somewhat like they do in the problem. And once they're clicked together, they're really hard to move. All right. Yep. They just really want to attach here. All right. Okay, now here come the wires. Yep. So there's one. There's one. Actually, didn't have to do it as complicated as I did. This looks actually almost worse than what I tried to do. As far as the aesthetics of it goes. There we go. Okay, I think we can see that this is the way it looks like. Alright, and here's the battery, and I have to check is the battery to the left or the right. Up, the positive is to the left, so I got it. And then, yeah, that'll be okay. Alright, oh yeah, and then I have to change all these resistors. 40, 20, 60, 70, 50. So 40, 20, 60, 70, and 50. There we go. Okay, and then I take a voltmeter and I actually put it on here. So there and there, and actually we already got our answer as 0.42 volts with the higher potential here. We can see how the electrons are flowing. There isn't much going through here. Apparently it's, oh, I forgot one thing. Oops, that's 20 volts. Not 9. There we go. Alright, so actually it's 0.94 volts. Actually, it doesn't matter if I put it here or there. It's 0.94 volts either way. So that's the answer with the positive one here and a negative one here. That, of course, is with the construction kit, but I need to show it the proper way, which is using Kirchhoff's rules. Alright, of course, as far as those are concerned, we are going as far as those are concerned, we have a number of loops and we have a number of junctions, and we also have a number of variables. Those variables that we would have would be the currents that flow through each one of these resistors. So we have 5 unknowns, respectively, of course, for each current. Once we multiply it with the resistance, we get the voltage. So if we call these that we have 5 unknown currents or 5 unknown voltages, either way, it's not that we have 10 unknowns, we have 5. There's also a 6th one here, which is the current that flows through here, but I don't want to introduce that 6th unknown, because once I have these 5, I could figure out what the 6th one is. So we'll just leave it out. We have 5 unknowns, the currents that go through here. For these 5 unknowns, for which we technically only have to determine this one, but there's no way around it, we have to find equations that simultaneously compute all 5 of them, and then we single this one out later on. We need 5 simultaneous equations. Well, let's see what we got. We got a junction here, we got a junction here, and we got a junction here, and we got a junction here. That was easy. We have 4 junctions. How many loops do we have? Well, let's look at the triangle here on the left and a triangle on the right, and then we have this diamond here. So those are 3 loops. And then we have a number of loops that actually go through the battery. The top one, so that would be the 4th. The bottom one, that would be the 5th. Then we go through here. Watch this. Kind of a squiggly one going up. That would be, I believe, the 6th loop now. And then we have the squiggly one going down, and that would be the 7th. So we have 7 loops altogether, and 4 junctions would make for 11 equations. We could use them all, but to figure out 5 unknowns, that would be an overkill, so we would have to focus on just some of them. First of all, what I'm going to do is I label these here. It pretty much according to what we see here with the plus being over here and the minus over here, it would make sense to label these here as plus, minus, plus, minus, plus, minus, plus, minus. Only the one in the middle I would know. I would have to choose plus, minus, or the other way around, plus, minus, because I don't know it to begin with. That's really not known at this point. The other ones are probably the correct guesses. So this one here I have to make a choice. I'm going to choose it like this one here, plus, minus, even though in the FET we just saw a moment ago that the positive is at the other end, so it should be actually switched. But what I want to show is when I'm done with the calculation, we will see that the result that we get comes out as a negative, and that negative will then mean switch those two. Okay, so as we go through here, I'm gonna put the arrows on. Let's see, I want to choose maybe a green arrow for the current. So according to what I just chose, the currents are going to go through like this. So lots of drawing, and on second thought I should have actually made this a little bigger, right? Oh well. Okay. Now here are 2 junctions. Let's separate this here. 2 junctions that I'm going to look at, which are junctions B and D. The reason I'm not going to look at A and C is because if I have a current flowing into A and then coming out here, that would mean I have to introduce the total current, which would introduce a 6th unknown, and I want to leave that out, so I'm just going to use B and D. Okay, here's what I'm going to write. Through the junction B, I have a current of I-40 going in, and I have a current of I-60 going out and I-70 going out, and I labeled them here with these here, so I don't have to call them I1, 2, 3, but I call them I-40, I-60, I-70, just referring to the resistance. This number here at this point does not figure in. This is just a current of some value that I don't know yet. So I-40 equals, let's see, I'll write this here. Oh, that'll work. Equals I-60 plus I-70. Okay. Respectively, if I subtract both I-60 and I-70, then I have to subtract them on the left-hand side, and that's what I'm going to do. I'll tell in just a moment why I do that. So I subtract them both on the left-hand side from the I-40. Actually, hold on one moment. Let's start that over again. I put a negative right here, so there's a minus. And yeah, I'll show you in just a moment why I did that. And then, of course, equals 0. The reason why I do that is, having it in this format here, is that I already get kind of my matrix out of this one. You know, the I-20, there was no I-20 and there's no I-50 going into junction B, but I leave a space here so I can come up with a matrix more easily later on. Junction D, there is a current I-20 flowing in. There is a current I-60 flowing in according to my definition. And there's a current I-50 flowing out of it, so actually this would have to read equals I-50, but I subtracted. And when I subtract it, I might as well put it right here. Okay, and then that of course equals 0. So again, the reason why I do it the way I do it is that it's convenient, and I will have a matrix here pretty soon. I can readily type it into my calculator and solve it without having further steps that possibly I could make a mistake on. I'm pretty sure that I got it correct right now. Alright, now I need the junctions, and I just had the junctions. I need 3 loops, and among the 7 loops I described earlier, I have to make a decision which ones I want to use. So for the voltages, I'm going to use this triangle here on the left. I'm going to use the triangle on the right. So right triangle, or triangle on the right, and the triangle on the left. Okay. Notice that I will not use the diamond, because if I put the triangle on the right together with the triangle on the left, well, I get the diamond. So that one would be redundant. It wouldn't give me any more information. Then after that, I'm going to use the bottom one through the battery. And notice that if I use the top one through the battery, on top of that, well, then I can just use my triangles together with the bottom one and get the top one. So again, that would become redundant, and then with the remaining loops, they would also be redundant if I put the other loops together. So as I said, I'm going to use the right loop, the left loop, and then what I perhaps could call the bottom loop, respectively. I could actually label them. I should label them. Actually, instead of calling them right and left triangle, I should label them as BCD. BCD, that's the one on the right, and ABD, that's the one on the left. and the bottom one is ADC together with the battery. So battery, and what did I just say? ADC. Okay. So B, C, D. Okay, that would mean across the 70 ohm resistor, I would have a drop in potential. So I'm going to have negative the voltage at the 70 ohm resistor, which is negative 70 I70. Then I go, so I went here, now I'm going to go this one here, and I have a potential increase, so I have a positive 50 times I50, so 50 I50. And then as I go back to B here, I also have a potential increase, so I have 60 times I60. Oh, it's a positive number. And when I'm once around with my loop rule, I come to the same potential, and so therefore going once around, the potential difference is 0, and of course I come up with 0. ABD, potential goes down, so I have a negative 40 times I40. By the way, on any of these where it didn't write a negative in front, that should be a positive, so here it's a plus, there's a plus, here's a plus actually as an equation. Actually here it's kind of better if I do write it, because I still have equations there. Okay, so negative 40 times I40, then this one here goes down, so it's negative 60 I60. Whenever I attempt to write something here, it's just too tiny. It gives me that some kind of circle here on the tablet. Makes it kind of strange. And then I go up here, going back to point A, going up here to through the 20, so I'm going to have positive 20 I20. Okay, and again, once around the loop would come out to 0. All right, now I'm going to go through here, and I have a potential drop, and then I'm going to have going up here 20 volts. Okay, so let's do that. I'm going to have negative 20 I20, and then I go down here, potential drop, negative 50 I50, and then I have 20 going up. Whoops, it was supposed to be a point, but I have plus 20 volts, and that equals, again, I went all the way around 0. Of course, there's no space for the 20 volts here. Notice that everything on the left-hand side is in currents, so I'm going to take the voltage to the other side, and I'm going to write there negative 20 as I do so. Negative 20 volts. Okay, here are my 5 equations in the system of equations that I have in 5 unknowns, so I should be able to solve them, and it's going to be a whole lot quicker if I do the matrix on the graphing calculator. I'll do that in a moment. Just a word here, if I had used other loops, if I would have written my junctions differently or the loops differently, as long as I do it correctly, I would come up with the same result. So this particular system of equations is not unique. I could write it differently depending on if I had taken my loops in a different way, but the result at the end will be the same. So if you do it slightly different on a different problem, don't worry which loops you're going to take, which junctions you're going to take, because you will come up with the right result as long as you do the algebra and the math right. Of course, again, here I didn't choose this particular junction here because it would have introduced a sixth unknown. All right, so let me extend the page, and I can readily write this as a matrix. And let's see, I need enough space here. Will some of this be a little bit? Oh, might be just a little bit out of the picture. All right, so here I have a 0 and a 1, a 0, -1, -1. I'm looking to a very top there, 0. This is kind of where I'm running out of space. And then I have a 1, 0, -1, 1, 0, 0. And then for loops, 0, 0, 50, 60, -70, 0, 20, -40, 0, -60, 0, 0, and I scroll this a little up, -20, 0, -50, 0, 0, -20. Of course, somebody could say on the last one I might as well get rid of the negative on each one of these, but oh well. Let me just double check that. So I have, here's -20 down, -50 down, and then here's the, yeah, that's actually 20 up, but it would be on the left hand side. When I get to the right hand side, it would be negative. Then this one here was the loop on the left hand side, so that was because I went this way here counterclockwise, it's 20 up and it's 60 down and it's 40 down, slightly out of the picture. And then on the right hand side, that was I went counterclockwise, so that would be 50 up and 60 up and 70 down. And then the junctions would be the junction D, the 20 is going in and the 60 is going in and the 50 is going out, so that's why this one here, and then that would be on the other side, so I have to subtract it, it becomes negative. And a junction B, this one is going in, so that's positive. These two are going out, they would be on the other side, but I have to subtract them, and that's where negative ones are. All right, graphing calculator. If you don't have a graphing calculator, you may have to go the hard way of doing these here as simultaneous equations or on paper. I have the luxury, and many of us do have a graphing calculator for this class because in algebra it was already required. And a trick, you might have used them also if you have already taken trig. Alright, let's do this one here. Actually edit, go one down. I think this is a 5 by 6. And now I have to see 0. Plug in all the entries. Okay, so I just put in 30 entries and cross my fingers that I put them in all correctly. Let me see. Yeah, the first column looks correct. The second column looks correct. The third one looks correct, as long as I didn't make a mistake on paper. The next one looks correct. So on 30 entries, you know, what's the probability on doing something incorrectly? Probability is higher than if I only had them plugged 2 or 3 numbers, but I had to plug in 30. Okay, let me give it a try. What do I want to do? Oh. Okay, I calculate, and that's a double REF. There we go. And there we go. And I go over here, and the one that I was supposed to compute is the one in the fourth one. So the 60 for the 60 ohm here, and this one here is negative 0.015625. That's the electric current that goes through it. Multiply that by 60. So I'm going to do negative 0.015625. Again, I was supposed to look at the I60 here, the one for the middle one, and that of course shows up here right there. There is that variable and comes out right here. And that's the current in amps, and I have to multiply that with 60 ohms to get the voltage, and just like I showed on FET earlier, that's negative 0.94 volts. So here I'm going to write, let's see what color. This one here is going to give me I equals so many amps, and from that I'm going to get that volts equals, actually I should say 60, there we go, voltage equals I60 times 60 ohms, and that equals, well, the negative 0.94 volts, and that negative then tells me that this one here actually needs to be turned around. So actually this one here is a positive, and this one is a negative, and then this one here, the current actually flows in that direction. That's what that negative told me. Long problem, because the Wheatstone Bridge is not easy. It takes quite some effort and time and algebra skills, and I'm glad I'm able to do this in a matrix, because you could imagine if I tried equations, elimination and substitution, this would have taken way longer than the 28 minutes that I have on the clock here.